I'm really pleased to be able to give this talk today, kind of tell you what I've been thinking about for the last year or two. And before I do that, I really need to recognize all the people that have really helped me prepare for this point in my research. And so I'm going to be featuring the work of Vahid Adikan, Alexander Bruchkin, left his end off here, Brian Jackson, Margaret Lenska, Ching Li, who assisted me a lot in the preparation of this talk, Shailin Liu, whose work I'll feature along with that of Elizabeth and Larry McCandlish, Kate McCulka, Christina Masad, and Magda Lenska, Pascal Pinceloop, and some collaborative work with Jerry Shen, as well as Eugene Zolotenkov. All people have spent nice amounts of time to work with me here at Rutgers. And the work here was made possible through support through the Office of Naval Research, Center for Ceramic Research, and ASIA Corporation, at least ASIA Corporation for today's research. So I'm going to go through some rather obvious things for people who are in the material science department. That is, what are ceramics? Also, I'm going to go through what do we actually mean by green, and then a little bit of background in the ceramics, as well as ceramics contribution to not only greenhouse gases, but also what it has to do with energy, but more from the manufacturing standpoint, its impact on that. And then some of the incremental innovations that might help make ceramics a much more green manufacturing approach, as well as some suggestions for some disruptive innovations, and then a brief sampling of what I've got going on here at Rutgers that's moving in that direction. So what is this thing called green manufacturing? Well, it's related to this whole buzzword these days called sustainability. Okay, so we have this multi-step process for making. If you just start with the raw materials, even the raw materials themselves are very frequently not green. Okay, when you start with minerals, aside from the environmental damage of mining, to worry about all the energy required to mill materials. And roughly about 0.5% of our full energy consumption in a nation is spent grinding things. So this is a big energy factor because of the huge amount of material that we dig out of the ground. Many of these minerals are carbonates, by the way, and that's going to be important because when we talk about industrial chemicals, a lot of times we do reactions at high temperature with solids, gases, heterogeneous phase, also liquids. There are some processes where, other than precipitating these things, we may use electrochemistry. For example, potassium hydroxide and sodium hydroxide. A lot of people think that's a green chemical. It's far from green. It takes a lot of electricity to make KOH before it gets to us. And it's a very energy inefficient process to do that. If we're making different kinds of single component materials, a lot of times we'll want to calcine them before they're ready to be used as ceramics. So most frequently, they're in carbonate form and they release CO2. And that's a big deal. You're going to see that almost the same amount of CO2 that's released in the calcination stage equals approximately what it takes to fire the material. So you literally, when you work with a carbonate, double your CO2 that actually comes out. So when we go look at something like barium titanate, very frequently made from a material that's either from carbonate or oxalate origin. There's roughly half of all of its weight loss is pretty much CO2 emissions. And then, like I said, you burn almost as much petroleum or some kind of hydrocarbon to actually make this final product. And we're only in the powder stage at that point. Then we've got to grind this stuff just like we had with the original minerals. And then after we're done grinding it, we do a high temperature reaction, as I mentioned. In this case, you may actually go through, in many cases, 2 different high temperature reactions before you're done, which would actually add another 30% more CO2 to the air. So some people get around that by spraying things into high temperature furnaces, but then you're spending a lot of energy evaporating water in addition to all the other stuff I already told you about. So we think about energy and we think about sources of CO2. We have decomposition of organics and carbonates. We need energy to power the mills and furnaces. And the magnitudes of these things are significant. Now, if you're actually looking at the firing step, now that we have the raw materials, we haven't even made the monolithic ceramic body yet. We don't have the dinner plate yet. We can choose to cast it, which means we're going to mix it with water and spray it. Sometimes this spraying stuff isn't such low temperature. Here's a gunning mix that's actually sprayed at a very high temperature, around the temperature that steel is made. These ramming mixes are actually ones that don't require high temperatures, but they're usually used for high temperature furnaces to fire other things, and they rely on the hardening at that high temperature to give it its high strength. Glasses and single crystals are made by melt-based processes, quite elaborate, quite energy consuming. If you're not going to melt, then you're going to go some fraction of the melting temperature and either work with glass or polycrystalline materials. And either way, you're just spending a lot of energy doing all this stuff. So here's the surprise. It's drying and firing that contribute a lot of the energy consumption. Roughly 30% of the cost of a ceramic is put into the energy for drying and firing. 30% of that energy that I'm mentioning here is spent drying, and it only takes double that for firing. And that's the reason why, even though drying is a low temperature process, it's because that the length of time required in drying is so much longer than a firing step that your energy consumption can in fact be comparable. And these are some of the numbers that, of energy that you might consume per hour, and they're on the order of gigajoules. And when you're doing this process, maybe if you're lucky, 20% of the energy is actually going for the process you're trying to heat. So there's a lot of problems with this, and as you can see, when you build a furnace like this and you have all these bricks, you got to heat all that stuff up before you're ready to actually get some work done making the ceramics actually densify. So I painted a pretty grim picture of what ceramics are in terms of energy, but here's the part you probably didn't expect. If you look at energy intensity for different materials, aluminum is by far the worst. And maybe that might surprise you because you think, well, gosh, all you have to do is extrude the aluminum. But when you make the aluminum raw material, you expend a lot of energy in an electrochemical process to actually make the aluminum raw material that's used and ultimately cast. And plastics is not too far behind that. So even if you look at them from a recycled standpoint, there's a huge energy intensity factor. And then ceramics fall, but look at the difference. It's almost a factor, well, it is a factor of 5. And steel is a little bit below it, which to me is a little surprising. But right behind it, it's cement, glass, and concrete. And so the only reason concrete is way down there is because it's really about 12% cement, and then you have 82% rocks that you dig out of the ground and grind into lots of little pieces. So let's pick on cement as something to look at. What's its contribution? In terms of all the CO2 that's generated based on natural gas and fossil fuel, the world in 2001 released about 24 gigatons per year. So that's a pretty large number. And the US is responsible for about 6 of that. So we're up there as far as accounting for 25% of that. China is like really moving fast. They are way, way higher than us. I don't remember the exact number right now, but just in cement alone, they account for half of cement's production. And so that's about, cement's production this year was 2.8 gigatons. China's responsible for half of that. So they already have about, just in the cement industry alone, half of 2.8, 1.4. So what's cement like relative to other CO2 emitters? Well, coal-fired plants, pretty large number, 8 gigatons, okay, in the United States. Cement plants are about 0.9, okay? So about a factor of 10 between the power plant and a cement plant. So cement doesn't account for a huge amount of the CO2, but it's still significant. Look at steel mills. Steel mills are lower than cement, but the thing you got to keep in mind is look at the number of sources. It's almost an order of magnitude different. And actually, a steel plant emits as much as a power plant. So if you really go gangbusters and building lots of steel mills in this country, we're going to really have a serious CO2 problem. Okay, so what's interesting is if you look at the metrics on CO2, more CO2 is released than materials in a single year. So here's cement here in terms of the CO2 number for 2006. Here's iron ore, bauxite. Now these quantities, let me clarify. These are the amount of material that are actually being made, not CO2. So if you look at 24 gigatons and you take all the bauxite, all the iron ore, all the soda ash, including the stuff you may use for making baking soda and all that, and silicon, it doesn't come close to adding up to this number. So that's, just think of it in terms of the US alone, okay? If we think of these are world numbers. The US's portion was 6 gigatons. It's still larger than all this added together. So cement's, really topped the list, at least in the ceramics group. It accounts for about 5% of CO2 in the world. In the US, the number drops to 1%. It's only because the efficiency of the furnaces is greater, so you're getting more energy out of your hydrocarbons than in other parts of the world. And ceramics and glasses place second, but that's kind of a guess. I just can't get any numbers on that right now. So if anyone's seen an article that really talks about specific metrics, I'm interested in doing that. But we'll definitely be looking at calculating it ourselves if we're not able to find it. So this is the cement process. I'm not going to walk you through the whole process. I'm just going to show you the nightmare portions of it. Here's a rotary kiln, okay? These rotary kilns can be literally as long as a quarter mile, okay? They are really big furnaces. They're in a diameter. It could be something as large as 18 feet in diameter. And you're taking, in a wet process, something that you're drying, and by the time you get to the end of the process, you have these big chunky stones bouncing out there called clinker, and those things actually need to be ground up. So here's the mill here. You also need a mill at the beginning of the process as well to conditioning all the raw materials. So all the grinding here and all the grinding here, as well as the high temperature heating, makes cement really, really ungreen. And here's some numbers just to tell you. And the thing to pay attention to is that I'm talking about concrete here. Okay, so I'm adding in all the energy required for digging up all the stone that you're going to mix with the cement, and then all the energy required to make the cement itself. And what you find is if you look at all that, including, hey, get the truck and drive it to the location, okay? We haven't left anything out here, the energy for the mining as well. I already told you the energy required for grinding is huge, but it's not compared to the energy to heat the kiln as well as the kiln reaction. So let me tell you a little more about this kiln reaction. It also takes a significant portion of energy as well. So this is CO2. So you can see the kiln carbonate decomposition reaction that I mentioned earlier before, and the CO2 from the fuel are really comparable numbers. And the fuel, just for that firing step, just overwhelms any other step, whether it's the transportation or the mining or anything. So here's the breakdown approximately. Everybody has their own way of tallying it. Henrik van Oss, I think, has one of the nicest papers that looks at that. So for the CO2 released from carbonate decomposition, it's about 1/2 ton of CO2 per ton of cement, okay? And for the fuel, it's about 0.43, but don't forget to add the electricity for running the mills and everything. So it's roughly 50-50 if you want to divide these into two. And then the energy is somewhere between 3 to 6 gigajoules per ton of cement. That's, that's a fair amount of energy, and you can remember some of the numbers I mentioned earlier. It's not terribly far from that. But it varies on the efficiency, and basically it's how old your cement plant is. The older it is, the less efficient it is. Now, you'll expect to see this for any other ceramic manufacturing process, if not worse. It's just that nothing equals the quantity of cement. When you're talking about megatons for some of the larger ceramic markets, and you're talking about gigatons for some of for cement, it's a factor 1,000 different. But the other point I want to make is that if we wipe out cement and the ceramics industries, it's not going to solve the global warming problem. But the biggest problem is that all the regulations and things like that come up, which I'll talk about a little later, is going to sweep the ceramics industry in, and it might end up sweeping the business out of this country unless something's done. So the percentage is an important wedge. It's not a big wedge. It's going to be a tiny little slither. But still worth doing, because all I know is that if I want to continue the work here, I'd at least like to have a few companies that I can send my students out to work for. It's not going to happen if all these other things happen. So what are we going to do? Let's just talk about CO2. I mean, it's kind of obvious, with energy. We saw gas rise to like $4 a gallon and more. You can imagine what that does to a business. It only gets somewhere between 3 and 27% of its energy to actually heat the solids up. That's kind of an obvious thing. That's something that you normally think about. But what about this CO2 thing? The two terms you're going to hear about is cap and trade and the carbon tax. Nobody wants anything like that who's in business, because in the cap and trade, someone's going to decide how much CO2 you're allowed to release. And if you can stay under that number, then the stuff that you haven't released, well, you can go trade it with somebody else and they can pay you some money for it that's hopefully less than the penalties for going above your allowance. The other way of doing it is, rather than giving everybody an allowance, right, we're talking about a carbon tax. So if you don't want to be taxed, don't release anything. So there's this whole game, which I could do a whole talk in itself, called capture and sequestration, or what they call carbon capture and sequestration. The term you'll hear is called CCS. And sequestration is nothing more than storing the CO2 somewhere, as long as it doesn't go into the air, okay? Air meaning anything above the ground, okay? Because I'll show you what people are actually proposing to do and what the DOE has endorsed 100%. And some of it's pretty surprising when you think of all the details that need to be worked out. But in any case, either of these things really give a strong incentive to develop technologies that have what's called a low or a small carbon footprint. That is, how much CO2 do you plan on releasing? Okay, like for example, if you drive your car a mile, you've just released something like 3/4 of a pound of CO2. Okay, that's your contribution when you go to the store. Your footprint is definitely not negative. Nobody's is here. So what does the carbon tax done to the rest of the world? Because we are behind in a big way. Sweden has been doing this for a long time, and they've seen, a 20% emissions drop as a result of having a carbon tax. And this is what they're paying for this, okay? Now this might sound like a lot, but I'll give you some numbers in a few minutes that will show you that, you know what? This might even be a deal when you consider the true costs of capturing and storing carbon. Finland, lower price, smaller reduction, approximately same time frame. Denmark, 15%. Norway's interesting because they're actually got an increase even though they got a $65 tax, but that's because they've become much more of a manufacturing entity than they ever were before. But as you'll see, they're getting really good habits. And Canada is just the first on our side of the block to come up with a tax, and we're still trying to decide what to do about all this. And here's some numbers on emissions. So if you're curious how many pounds of CO2, if you know your gas mileage, you can calculate it for yourself. And if you think about coal, since it's used quite often for power generation, here's some numbers that you would end up paying, at least if they end up having some kind of CO2 tax that the electric company is surely going to pass on to you. Actually, it's going to be much more than that, because this is all what the government's charging. I'll show you some more bad news in a few minutes, but just do a quick calculation. If you have a $12 CO2 tax, for cement alone, that means $37 billion at 2009 production. So that's a lot of money to add, or in other words, roughly $6 a ton. And you easily use a couple of tons if you're putting in a couple of sidewalk pieces. So this is what people envision doing. They take the CO2, and it's very much what they do with Sodapop, okay? They use an amine, and the amine catches the CO2 because the amine is basic and the CO2 is acidic, and it forms what's called an adduct. Basically, the two molecules just hug each other in the liquid, and they don't really want to go anywhere. They just sit in the water, and we throw it through a stripping tower that makes the amine separate from the CO2, and then the CO2 goes to a pressurization tank where they pressurize it to about 2,000 psi. And what they do at that point is they send it out to a pipeline. This pipeline goes out a couple of miles off of Norway. I've seen pictures of this, but I didn't want to inundate you with photos. But they take this 2,000 psi line and they inject it way underground. And they use it to force out methane gas so they can get more gas out from underneath the ocean, but they're also storing it, and a lot of the rock that's here is able to react with the CO2 and keep it nice and stable. So this is way below the ocean's floor. And they have actually successfully done this, and they actually store an enormous amount, about a megaton a year. And they're making this work, and they get about 100K a day in carbon tax. So it's a good deal. They're making it work. But let me just tell you a few things about this system. I don't even know what this costs. I don't know what the government spent for that. But I can tell you that if you run a power plant where you use this Sodapop approach towards pulling the CO2 out and compressing it, it's going to raise your electric bill by 65%. That's the estimate right now. And if we're lucky, maybe only 33%. So if you think about the numbers that I showed you with the carbon tax, it's actually a much smaller price than what it actually costs to really store this stuff. And that's because it takes a huge amount of energy to strip this CO2 from the amine and to pressurize it. You've got to run machines. You've got to heat things. You've got to run compressors. And that comes from the electric power plant. And so that takes all the electricity out. So now that I've painted this really droll picture, there's no hope, right? We can't fire these things. We've got way too much energy to pay for. We've got way too much CO2. Nobody has a good way of putting it underground. By the way, the DOE thinks we should bury everything underground. And the lawyers have really sharpened their teeth on this because they want to use, for example, old mines. And that sounds like a good idea, except you never know exactly where all the holes are. And there are instances where pressurized gases have actually gone out of some of these mysterious openings and created gushers in lakes and other places. So it's not that easy. And there's discussion, by the way. You know, there's a cogeneration plant in Linden. There's conversations about having a 2,000 psi line going out to the Atlantic Highlands. And there's a beautiful basalt formation way under the ocean where, for just the price, I think it's somewhere, project cost of about $4 billion, we can get that line out there and start injecting. I'll bet you anything, if it's anything like the Big Dig up in Boston, I count on it being 50 billion. Okay, so what are we going to do about ceramics? Because, you know, I'm wondering, maybe you're going to get rid of our department, all this talk about industry going out of this country. But if we use minerals and waste products where we can, that's going to be a big helper because we've already expended the energy to use these things. And there's lots of minerals that don't require very much in the way of grinding. And also just minimizing the need to grind. You know, don't grind any more than you really have to get your process to work. And then there's a whole game of reducing processing temperature and improving process reliability. A lot of ceramics manufacturing, maybe 50% yield on the product, so you threw all that energy in the garbage instead of utilizing it somehow, as well as the CO2. Get rid of carbonate reactants because they just release way too much CO2. The reality is, though, if there's any traditional ceramics people out in the audience, they know they can't live without this stuff because everything else costs too much because carbonates are so damn thermodynamically stable, they're just all over the place. Find a way to eliminate the need for water. It's kind of funny how we work with ceramics. We add water, then we evaporate it, then we add it again, then we evaporate it. And water is very energy intensive. But find ways to minimize the number of steps where you have to do something like that. And don't use organic additives because they're going to release CO2. And the other thing is a lot of times we're mixing things really poorly If we mixed them better, we wouldn't need as high a temperature. And we wouldn't necessarily need milling as well. So what can we do on the forming side of it? Well, we can learn how to pack particles better. Here's a packed array of silica that we've made in our lab. I'll tell you more later about how we do that. But you can reduce a lot of energy in the forming process and the firing process if you can get packing like this, because you never see anything like that. The question is, how do you do that and still minimize the CO2 output? Because a lot of these fancy chemicals that you might use for making these compounds are really far from green. They're much uglier than the stuff that I've already told you about. Also develop net shape forming processes so we don't have to grind our materials to their final shape. So those are some of the things. From a thermal side, why heat all this brick in a furnace? Try to reduce the mass of brick. Use alternative fuels. Directed energy is a way of not heating brick, maybe concentrating the solar rays or using microwaves which couple directly with the material you're firing and not what the furnace is housed with. Reduce the firing temperature by improving the mixing. Again, just stop using water. Maybe you can do drying, fabrication, and firing in one step in a way where you can save energy. More stuff. Just lots of things we'll associate with equipment. This is kind of the summary. Lower the temperature at times. These are all things I mentioned already. Get the rejection rate down. But here's some disruptive things. So this is where there's lots of really neat stuff to do. Avoid CO2 generation, or minimize it at least, by some of the things already mentioned, but there's other things we can do which I'll show you. And try consuming CO2. Try taking some out of the air instead. And try making some drastic changes in processing temperature. And try to make things that actually perform better than the stuff that's made the conventional way. It's just like painting in your house. If you use the oil-based paint, it always comes out better than the water-based, but it's bad for you, it's bad for the environment. But people still all know it comes out better. But if you can make materials that in fact are actually better, then people won't see being green as having a cost associated with it. So that's where the research opportunities are. So here's something, maybe instead of, working with big pieces of marble, mix the calcium carbonate with a polymer to make engineered marble. These kind of processes head towards carbon neutrality, but they're really not making any kind of a huge impact. Moving along, there's better practicing examples like in glass manufacture where people take waste glass product and throw it into a glass batch to improve the glass manufacture. And the energy savings in terms of money in energy and disposal is very significant. And it also reduces pollutants as well. Electrical power consumption, if you just make the motors and drives systems that you use more efficient, you can save a lot on electricity. They're using photovoltaics. Here's the kinds of metrics on tons of CO2 that's saved. Fuel cells, cogeneration, in other words, locate your plant where you want to generate electrical power. And then this other area, which really is a big potential in the US, is recovering the heat that you throw into the air. Instead of seeing these smokestacks with lots of stuff coming out, attach a pipe onto it and try to collect that energy. And if you can do that, you can provide, in savings, 19% of the nation's electricity. So that's a big number. And the technology's here, and it's far from being implemented. So let's go into materials technologies. Drywall. There's drywall that is currently made in a way where you have to heat the plaster of Paris to remove some of the water crystallization, as well as drying the material. It has a huge energy impact. If you can avoid that step, which a company called Serious Materials has achieved, you can get 80% less energy required and 80% less CO2. Still CO2 positive, meaning it produces more CO2, but it's an improvement. It's making it easier because you're using less energy. That lowers the cost as well as the CO2 footprint. Well, there's a company called Skyonics, meaning using the sky as a mine. And here they're making electrochemical sodium hydroxide. So this sounds like a pretty cool thing. You make sodium bicarbonate. Here's the thing. Worldwide production of sodium bicarbonate is 42 megatons. So all you need is 6 power plants and you've produced the world's sodium bicarbonate. They're done. You can't do any more than 6 plants unless you can find some new uses for the stuff. Also, what are we going to do with all the chlorine and hydrogen gas? Well, I know what I do with the hydrogen gas, but the chlorine is roughly dependent on how much plastic you sell. And that's where most of it goes. And also, there's a huge parasitic energy loss by making the sodium hydroxide. And so this is a real nut and shell game. Everybody comes up with some new way of doing something, but they don't factor in what the impact of this is. And that sodium hydroxide is huge in terms of the amount of CO2 is. And I don't actually know what the number is exactly is, but the cheapest you can make this stuff is somewhere on the order of about 15 cents a pound, which means that a ton is about $300. If you're going to make any kind of useful material in the cement industry, there better be fractions of $100 a ton, not 300. And that's just the beginning. Alcoa, in the process of making aluminum, generates lots of CO2 by consumption of their carbon electrodes and all the electricity that's used. So they have this material called red mud, which is a product of the process. It's basically mostly iron oxide and some sodium hydroxide. And so people are using that as an additive to cementitious materials. And because it's highly basic, it also pulls CO2 in. So there's a lot of effort in Australia. Right now, they're taking in about 70,000 tons per year, and they're going to be bringing it up to about 300. So this is significant, and this is used as a filler for road beds, building materials, and even just conditioning soil. Perfectly safe because the CO2 is neutralizing the sodium hydroxide. And then there's another area of cement where people are calling this technology accelerated carbonation, where you're basically putting CO2 in a gas, and while the cement is curing, you're actually adding the CO2. And this is just a cartoon of the cycle for doing that. But there's no way you're ever, even if you take all the calcium in, remember, even if you put all the CO2 back in the cement, you still have all that fuel you've spent, trying to heat that cement and make it a cement. So you're only going to cut the amount of CO2 at most by a factor of 2, but not get rid of it. People like to make magnesium-based cements. This is a company in Australia that's trying to commercialize this. At best, this is carbon neutral because what they want to do is take a magnesium carbonate, calcine it using the solar sun rays, then react it with water afterwards to get all the CO2 back. So if you don't count the energy of the sun, at best you have what's called a carbon neutral material. So that's the best they can do there. And then there's this company called Calera, which has an interesting idea. What they want to do is say, hey, let's just make an additive to concrete that replaces all the stone that we're putting in. And because it's made of CO2, because we use 88% aggregate and 12% cement, if we replace a lot of that aggregate with our new calcium carbonate, then we're going to be able to store a lot of CO2 underground, because after all, there's over 100 gigatons of concrete that are actually being made, so there's plenty of room for that. And so that gives them the excuse to make, once again, sodium hydroxide, which their selling point is, hey, we figured out how to make it 60% more energy efficient, but it's still sucking energy out of the power plant, and that's one of the problems. The other thing they're doing that's nice, though, is they're using brine from reverse osmosis for their source of cations. And then ultimately they're making this carbonate salt, which is the additive for concrete. So this is another way to kind of get around being green by finding some way of replacing something that can make the whole process appear carbon negative. Because you're storing the carbon in the process of doing this. But I still don't think their calculation is, they've placed no numbers on what the CO2 footprint is for making the alkaline earth hydroxide. They have to do this. You cannot take cations out of seawater unless you raise the pH to at least 13 or 14. And then the process of precipitating the solids lowers the pH back to 7. It's a neutralization reaction. So for every mole of material they want out as a carbonate, they're going to have one CO2 neutralized by a sodium hydroxide. So we'd like to see what that number is. Okay, so that aside, what are we actually doing? Well, we're working on techniques that use low temperature processes for making ceramic powders. And we can boast typically tenfold reductions in processing temperatures, and by controlling the size and morphology, we avoid the need for the milling, so we no longer have to grind things. We use water-based routes so that we can recover the water. In fact, we precipitate these things from aqueous solutions, which leaves you with clean water afterwards. Doing also some interesting work where we're not working with water, but we make these materials that require quite a bit of energy in the extraction and everything, called rare earth-based materials. And I have a collaboration with John Brennan, the chemistry department, who makes these beautiful colloidal molecules that have rare earths in them, and he can make them at room temperature. Also, we have work going on with composites where we're taking advantage of self-assembly and improving mixing. So let me just mention a few of these things. Here's some neat work that Vahid Adakhan did for his PhD, where we looked at this whole process of making barium titanate, BaTiO3, from this barium titanal oxalate. So an oxalate is actually two CO molecules joined at the hip, so to speak. And these metal oxalates are calcined. So for every mole of barium titanate, you get 2 moles of CO2. You usually have to heat this above 900 degrees C. The reaction time is at least 3 hours. You have to mill it. It's not very green. So one of the things that Vahid said to himself is, well, gee, what if I look at a way of doing it in water? So the way we start is calculating a phase diagram using thermodynamic principles. And so this shaded area here shows you where you need to run your reaction conditions in order to run this reaction, where we take an oxalate and we react it to form barium titanate. And this is actually an equivalent reaction. This is actually a single compound, but this is the only way we could model it. So this model told us if we add lots of KOH to the system, not only will we get barium titanate, but we won't release any CO2. And this is a room temperature diagram. So we were dying to find out if this thing actually worked. And lo and behold, in a few minutes, you can make barium titanate straight from the same raw material that industry says can only be done at high temperature and milled. And here's some examples of the powders. I mean, it's, this is a very good first result that shows we can make the particles small and spherical, and from here we can optimize a lot of the process. And this is a video that that Vahid had taken, which I don't think the safety people are really that jazzed about, but you'll get an idea of how thermo describes energy. So what he's doing is first he's adding the barium titanal oxalate to water, and then in the second step he's going to add the KOH to the system. And you'll see what happens once the reaction starts with KOH. So I think it's kind of self-explanatory. So he's just stirring this thing. It's mildly heated. And here it goes. Stand back. Okay, so if I had the sound on, you'd hear these guys acting a little scared of what just happened. But he just made barium titanate, okay? Right in front of your eyes. So we like to call this instant hydrothermal synthesis, or IHS. Okay, well, here's another example, making biomaterials. Again, here's a roadmap for the reaction conditions we need to work at. And this work was kind of interesting, some work done by Christina Massad for her PhD. And what she was looking at was, well, gee, how do we make hydroxyapatite at room temperature, but use compounds that the body actually wouldn't find poisonous at all, and do it at room temperature? So you could imagine making this material even in a surgery room. And here's, again, she did the modeling, and the experiment showed that she could make a material that is some of the smallest particle size hydroxyapatite in the world. It's about 2 or 3 nanometers. The material is so unstable that if you let it sit for 5 months, it does something that ceramists think are unthinkable. You go from a crystalline material to being an amorphous material, because there's so much surface there. There's more atoms on the surface than there is in the bulk, so the whole thing just goes disordered, and the crystallite size actually increases by a factor of 10. And so here's another one, just as a last example. We have a bunch of particles. Maybe we made them at low temperature. Instead of using high pressure, high energy equipment to assemble things, let's use self-assembly. So what we do is we take the particles, they're suspended in a liquid, we drop them onto a water bath, and we functionalize the surface so that the particles will float on water. So here we're floating something that's 8 grams per cc on something that's 1 gram per cc. We make it so non-wetting it can support its weight. So this is a material called lead zirconate titanate. And the alcohol inside this dropper, when it hits the water, spreads. And when it spreads, it delivers the particles to this raft. So think about this as like the bubbles, you know, when you're taking a bubble bath, how they like to assemble on the other side of the bathtub and form beautiful hexagonal arrays. Now we have these particles packing themselves into dense arrays, and if we put a glass slide into there, we can actually pull this material right off of the water to make a beautiful monolayer film. And so here's an example where we use industrial aluminum oxide and show we can pack these materials beautifully as a single layer of particles. So imagine this material as an epoxy coating on a floor. It would be very hard. It's the densest packing of particles in an epoxy, the one that you can achieve. And I'm not showing you the composite, but we are able to do that. Here's another example where we're using cubes, where we're packing the cubes. And here's an inset showing a natural material, which is just what the microstructure of pearl looks like. So we're beginning to mimic nature, you know, with these self-assembly processes. And here's another structure we made is a single self-standing layer having polymer. So here's a Cobblestone Road, and here's the material that we made that's about a micron thick. Again, all being done at room temperature, using basically nothing more than rubbing alcohol, water, and a Dixie cup and a glass slide. And there's that silica example I showed you before, and this was just kind of a neat picture I wanted to throw in that we can actually watch the particles assemble using a technique called particle image velocimetry, and working with Jerry Shan's group to learn how to do that, because these guys know all about how to image fluids. And there's some really interesting fluid motion that happens here, but I'm not going to talk about that today. So in summary, I'd like to close and just say that ceramic manufacturing can contribute a significant wedge towards reducing greenhouse gas emissions as well as reducing energy. But it's more the survival. The cost of the energy use and the CO2 emissions is what we really need to be concerned about, because the industry at $3 or $6 or $10, or if they actually tally up what it really costs to take CO2 out of the air, who knows, even $150 could make it impossible to build a business in this country. So we really got to figure out what to do about this. And impacting the short-term and long-term measures, I've proposed some of these, shown you some of the things that people are actually doing, and then some issue, hopefully I've made it interesting to you. It's at least really interesting to me that we've got a lot of really interesting ideas that we're pursuing now to try to make a difference, and hopefully a year from now you'll hear about what that is. So with that, I'd like to thank you for your attention. Does anyone have any questions? Yes, sir.
Maybe you said it. Repeat the CO2 versus wood, glass, and steel for buildings, or price and CO2.
Well, in terms of
Concrete versus wood, glass, and steel.
Oh, okay. If you look at the energy intensity of concrete, it's the lowest on the list. And aluminum is the very top. So there's about, in terms of energy intensity factor, there's a factor of 185. Repeat what you said again?
You showed it by unit mass, but if it's by volume or by structural need for the building or the other application, that should be different.
Yeah, well, that's true, and I don't know how those numbers actually meter out. But my numbers I'm talking about is just an energy intensity factor, but it turns out it's going to become more and more complicated to assess that, because you got to look at CO2 release or other greenhouse gases, as well as the energy, and like you said, how you actually utilize the material. There's all kinds of funny equations that people are devising, like people are talking about trying to put lots of slag, which is a steel-making waste product, into concrete, and the steel manufacturers that produce the slag are trying to think of ways of passing on the cost to those people for the CO2 and the energy, while everybody thinks who's going to get these waste products that they're going to get it for free because these companies are happy to sell it. give it to you. They're not happy to give it to you if they think it has value. And so it's going to be a pretty complicated thing. The other thing that's interesting in Europe that isn't happening here is that they're trying to set up standards for life cycle analysis, so you can really see all the different things that Professor Garfunkel is referring to. And it's really a complicated thing. I mean, there are people now who are working on trying to develop what those metrics are and how to do it. And that's a talk in itself. Anybody else? Okay, thank you very much.